Okay, I want to mostly focus on the normal distribution questions, but this first one, just to tell you, is an estimate based on the histogram here, where you're roughly looking at how many are in each of these bars, especially this 5 to 10 bar going over there, something around 100, and this 10 to 15 bar, something around 350-ish. It's 15.3% is Rockingham County, so you may throw in a few from this bar, but probably not too many there on average. And then you would just add those up, divide by the total number of counties. So number 2 is the first normal distribution question. We can do a real quick sketch of the normal distribution here. And we see the mean for all counties in the US is 24.2%. Rockingham County is coming in a little bit below that, so we draw a little dot there for that. What we really need to know is the percent that's excuse me, is below this, less than this 15.3%. That's what we're looking for here. So we can use Table A. We know that Table A gives us a percent, but we're going to have to give it a z-score. So in order to get that percent, we need to convert this 15.3% to a z-score. We need to see where Rockingham County falls in terms of the rest of the counties in the US. So we take Rockingham County's score minus the population mean, the overall child poverty rate for US counties, and divide by the standard deviation. Tells us that we're sitting at about 1 standard deviation below the mean, just under 1 standard deviation below. That negative 0.98, we then zip down right here. So we have the z-score. We're looking inside the chart here. So the negative 0.9 comes there. The 0.08 is from right there. And that's how we get the 0.1635. So that tells us that 0.165, or about 16.35% of the counties, have lower child poverty rates than Rockingham County does. And the only thing with that estimate is you do want to recognize that it was a slightly skewed distribution. So when we use this mean and standard deviation, we're thinking of a theoretical, a perfect distribution with this mean and this standard deviation. And so it did actually look pretty close to normal, and the reality is it is almost right there. But we can't trust it just because we're using numbers here. We do have to recognize that our calculations are based on a perfect normal distribution. And by the way, if you had changed these to decimal equivalents, 0.153, 0.242, 0.091, you would also get this exact same z-score. Okay, let's skip down to number 7 here. And I'm just going to do it for this version. Notice you may have the other version. If you do, use the PDF to see the exact numbers, the PDF solution, and you can use the video to see the process here. So we have these males who aren't typical runners, walk on a treadmill, and then get their heart rates. We get the distribution of all their heart rates as 130 is the mean, standard deviation 15. So it might be helpful to plot that really quickly. So 130 there is our mean. But what we really want is the cutoff between the lowest 80% and the highest 20%. So you see I have a line drawn in there, and that's just a rough sketch so that roughly 80% of the area of this normal distribution is to the left, 20% is to the right. So where do we go from here? We know that Table A is a conversion table. So if we have a z-score, it'll tell us what proportion of the scores are below that z-score. If we know the proportion below, we can get the z-score, and that's what we have here. We know that 0.8% of our men were below the cutoff. So we look up that 0.8 in Table A, and a careful point to note here is we're now looking in the center. These are the proportions to the left. These are the z-scores. So we now have this value, and we're looking for the z-score. So 0.8 would put us right between these two numbers here. So we're looking at 0.84 or 0.85 for our actual z-score. Putting either one would be perfectly fine. I'm going to use 0.84 here. And so that's our z-score. So our cutoff is going to be 0.84 standard deviations above the mean. And now we actually have the z-score, we know the mean, and we know the standard deviation. What we don't know is that precise cutoff, that x value in our case. So we solved this equation, multiplied both sides by 15. So that 15 will come over, get multiplied by the 0.84 to give us 12.6. And then since we're solving for the x, we add 130 to both sides and get 142.6. So that's the cutoff. In this large sample, 80% of the men had less than 142.6 beats per minute, and 20% had above. Okay, final one here. This actually, you could look on the other video I posted right above these solutions for the homework problem, but I did do this in a little more of a shortcut style, so let's see if this works better for you. Here's a drawing of what we have. We have these fruit flies. We're looking at their lengths, the distribution of their lengths. We know the average is 0.8 millimeters, and we know a standard deviation here. So we want to know between 0.75 and 0.90, we want to know what percentage of the fruit flies would fall in that range, would have a length somewhere between these two values. So what we want to do first is figure out the z-scores, because if we're going to use table A, we're going to need to come to the table with a z-score. We can't use these raw values of 0.75 and 0.9 on table A. So we convert each one to get a z-score. We're using that same formula that we used before right there. And that'll give us a z-score of negative 0.71 for this one and 1.43 for this one. We look those two values up on table A to find out what proportion is to the left. So we find out basically 92% of our distribution is to the left of this Z2, but we want to subtract off this chunk, which turns out to be this 0.2389. So if we subtract the two, we'll get the proportion that's right in between there, and that's our 0.6847. If you want to convert it to a percent, 68.47%.